Okay, Organic Chemistry 1. We just finished section 8.4, which dealt with Markovnikov addition of hydrogen halides like HBr, HI, and HCl. And so that was hydrohalogenation. And now we're going to cover hydration, which is titled section 8.5 acid catalyzed hydration. So you can imagine that we're going to need an acid to do the reaction. And it says here, I'm just reading right off the slide, it says the components of water are hydrogen and a hydroxyl, and will both be added across the pi bond, right? If you think about H2O, you can think about H2O as being this Lewis structure, absolutely. But you could also think about it as being a hydrogen attached to a hydroxyl. And when we do a Markovnikov addition of water across a double bond, and that's the Markovnikov regioselectivity, we're going to add the hydrogen to the carbon that is richer in hydrogens, and we're going to add the hydroxyl to the carbon that is poorer in hydrogen. So you see here we have hydronium, and we have an alkene that is unsymmetrical. We have this carbon that has one hydrogen attached to it, and then we have this carbon in red which has no hydrogens attached to it. And so the carbon in blue is the one that takes the hydrogen, and the other carbon takes the hydroxyl. And you can see that that occurs in a very high yield, 90% yield. Now it says here that sulfuric acid is typically the acid catalyst that is used. Now remember, the reason why we write H3O plus is because when we put sulfuric acid in water, right, the equilibrium is going to lie hard to the side of hydronium plus the conjugate base of sulfuric acid. Why? Because the pKa of sulfuric acid is around 9, whereas the pK of hydronium is equal to negative. I should have said negative 9. Where's my eraser? There we go. Negative 9, and the pK of hydronium is negative 1.7. So again, the equilibrium is going to lie most to this side. So based on the leveling effect, what you're mostly going to have in solution will be hydronium, right? We're mostly going to have hydronium. So the first step of the reaction, the proton transfer between the double bond and the hydronium, right, involves this proton transfer to form, son of a gun, I can draw better than that, to form rather this carbocation, which after nucleophilic attack and proton transfer is going to give us the tertiary alcohol. Now, keep in mind that the hydroxyl, again, is added to the more substituted carbon. This is Markovnikov addition. And the more substituted that carbon atom is, the faster the reaction is. Here, right? You see that in this case, there's no Markovnikov and AntiMarkovnikov to worry about when you're using ethylene as your alkene. But you see, as you go from propylene to isobutylene, the reaction rate increases dramatically. And why does that happen? Well, it's consistent with a carbocation intermediate being produced, right? As being the more stable the intermediate, the faster the reaction will be, because the lower the activation energy will be. This is the mechanism right here that I drew the first step already. And then the second step is going to be a nucleophilic attack followed by a proton transfer. And I have the proton transfer on the next slide over here. And there we end up with our alcohol. And so you should be able to draw out all the steps of this mechanism, including the deprotonation of the oxonium. And what do we get after the water grabs this proton? We get the desired alcohol, but we also end up with another molecule of our acid catalyst ready to go again. And that's why it's called a catalytic reaction, or we need a catalytic amount of acid. So let's take a look at the mechanism. It says here, draw a mechanism for the following transformation. Let's just do it very slowly. We're starting with an alkene. This carbon has 2 hydrogens attached to it. This one only has 1. So the carbon that I have highlighted in red, that's the one that's going to take the proton. Let's draw out a molecule of hydronium. So there's our hydronium molecule. The first step is the proton transfer, the double bond. We grab a proton like this, and then what do we form in the first step? Well, we're going to end up with a carbocation. So let's draw that carbocation like this. Nothing wrong with that carbocation, but we know that there's a hydrogen atom here, isn't there? And this is a secondary carbocation, and it can undergo a carbocation rearrangement Okay, it can undergo a hydride shift in order to give us a tertiary carbocation, something even more stable. Right, and the dead giveaway that was going to happen is because the hydroxyl was not attached to this carbon. So what's the next step going to be? Well, once the hydronium lost a proton, here we have water. So a water molecule is going to attack as a nucleophile. So we have our water molecule, and it's going to attack. So we do the nucleophilic attack like this. We're going to draw the oxonium that's produced. Just going to look like this. There we go, like that. Okay, and then the very last step is going to be another proton transfer. So we're going to have another water molecule come in. It's going to abstract one of these protons to regenerate the hydronium, and there you go. We have our tertiary alcohol like that. So again, what are the steps? Things that we've seen before many times: a proton transfer. Kind of the key step here is the carbocation rearrangement. Then we have the nucleophilic attack, and we have another proton transfer, and there we have it. There's the mechanism of this Markovnikov addition with carbocation rearrangement to produce the tertiary alcohol. Now, in terms of the thermodynamics of this reaction, of this hydration, it says the reactants and products of hydration are in equilibrium, and we can exploit Le Chatelier's principle to control this equilibrium. What's Le Chatelier's principle? It states that a system at equilibrium is going to adjust in order to minimize any stress placed on the system. So in a nutshell, if you take a look at the addition of water to the alkene, in order to affect that, we're going to do the reaction in dilute sulfuric acid, right? If there's more H2O, if the sulfuric acid is dilute, that means the concentration of the water is elevated, and that's going to push the reaction towards this side to give us the alcohol. If we want to make the alkene, then we use concentrated sulfuric acid, right? In concentrated sulfuric acid, it means the concentration of the water is lower, and so it's going to push the reaction to this side. So we can simply use Le Chatelier's principle to control whether we want the alcohol or the alkene. So again, if we want the alcohol, we use excess water, and when we want to make an alkene, we would use only acid. We would not add water, so we would use the most concentrated acid we could find. Okay, now another way to remove water, and chemists have all kinds of ways to remove water. We can use something called molecular sieves, which we'll never talk about in this class. But there's other types of, there's a type of glassware called a Dean-Stark trap, which can also be used to remove water. So again, what's the crux, right? The idea is that we have mostly water here when we want to make the alcohol, and we have very little water here when we want to make the alkene, just like that. All right. Well, what about the stereochemistry of this Markovnikov addition of water across a double bond? Well, you can imagine that if you form a carbocation, that the same thing that we saw with hydrohalogenation in section 8.4, right? If you end up with a carbocation intermediate, that means the nucleophile can attack from each side, right? If you draw the carbocation that's formed here, what is the carbocation intermediate? It looks like this, okay? So again, that means that the water can attack from either face of the molecule, right? Your water molecule could attack from the front face like that, or your water molecule could attack from the back face like that. And either way, you're going to end up with a racemic mixture. In this case, I don't know why I had to draw that, but anyhow, you get the idea. All right, so in this case, you'd end up with a racemic mixture, and then you'd have to separate it. All right, now I want to back up in the slides. I don't want to jump around too much, but there's something a thought I want to share with you. What if, like I told you, there's no way to avoid this, right? This carbocation rearrangement. If you just take this molecule and you treat it with acid, the carbocation rearrangement is going to occur. So my question to you is, or a question that we want to think about, and we're going to answer it in a second, is could we do the Markovnikov addition of water across this alkene and only get this compound? Let me show you what I mean. Could we just get this as a racemic mixture? Okay. So is there a way that we could avoid this carbocation rearrangement? And you can imagine that if I'm bringing it up, the answer is yeah, there's a way to do it. And the way that we do that is we use what's called oxymercuration demercuration. It's covered in section 8.6, chapter 18 on the brain today. Anyhow, it says here that Markovnikov addition, I'm just reading right off this slide. When we just do the plain Markovnikov addition of water and sulfuric acid to make hydronium, based on the leveling effect, has limited applications. Why? Because carbocation rearrangements can occur, and that gives us a mixture, right? If we were to take this molecule and just treat it with H3O+, the carbocation intermediate that you would get would be this. But that's going to undergo a methide shift to give you this, right? And then after the nucleophilic attack and proton transfer, you would end up with this tertiary alcohol. And so the question is, how could we just do the Markovnikov addition and avoid carbocation rearrangements? Well, we use special conditions that we call oxymercuration demercuration. It's the Markovnikov addition of a hydrogen and a hydroxyl, but there's no carbocation rearrangements occurring. So what do? In the first step, you use mercury 2 acetate, which is usually called mercuric acetate. So this is mercuric acetate in water. That's important. And then in the second step, you treat it with sodium borohydride. So this is sodium borohydride. Now, what's interesting about this reaction, besides the fact that it's an anti-Markovnikov addition, there's no carbocation rearrangement, and it occurs with a really high yield, is that the mechanism is not covered in gross detail in the class. Now, again, this is just rehashing it here. You can form a carbocation which can undergo a rearrangement, but what happens in the mechanism is that you actually end up with this mercurinium ion. So you have the mercuric acetate, and again, our book probably doesn't go into all the detail of it, but you have the mercuric acetate. I'll just draw the Lewis structure of it quickly. Oh, the AC means acetate. So you have this, and then it just decomposes to give you this guy, where you have a positive charge on the mercury, and then you have an acetate ion. So the bottom line is you have a good electrophile. So this is an electrophile. And then the double bond acts as a nucleophile, and you end up forming this really cool intermediate called a mercurinium ion. Now you see how there's a lone pair on the mercury here. So even though you get Markovnikov addition of the mercury, so to speak, right, it's adding to the carbon that is richer in hydrogens, it's got this lone pair of electrons which can dump the electron density down into the carbocation. So you kind of form this like three-membered ring that's called a mercurinium ion. And the thing is that a mercurinium ion is not going to arrange, unlike a carbocation, which will. This is never going to rearrange, no rearrangements, okay? So what's the fallout? Well, the mercurinium ion is going to react with a nucleophile. And what happens is it's going to attack the carbon. The nucleophile will attack the carbon that would result in the more stable carbocation. So it's going to attack the carbon that has the less hydrogens attached to it from the get-go. Okay, then you end up with this intermediate here. Then you treat it with sodium borohydride, and then it's not magic, that it just removes the mercury and the acetate, but it occurs via a free radical mechanism, which is not covered in chapter 8 of our textbook. Okay, so basically you take this and then you just treat it with sodium borohydride, and that will just remove this. Okay, like that, and then you end up with a hydrogen there in its place. All right. So again, the mercurinium ion doesn't undergo a rearrangement, but it is susceptible to reaction with nucleophiles. So again, if I had only 30 seconds to teach this reaction to you, if I said, you guys, I'm going to teach you section 8.6 in 30 seconds, here's what I'd tell you. I'd say, look, we covered this in detail in section 8.5, Markovnikov addition of water across a double bond. If a carbocation rearrangement can happen, it's going to. If you want to avoid that and you only want to get the product that results from no rearrangement, you use oxymercuration demercuration. Memorize these two steps. The first step, is mercuric acetate and water. The second step is sodium borohydride, in that order. Okay, and that way you just avoid the carbocation rearrangement, and that's all I would tell you, is just memorize it and know it. I'm not going to ask you about the mechanism. Okay, I'm not going to ask you about the mechanism of this. Then you might be saying, well, Mr. Dion, if you're not going to ask me about it directly, why did you put this in here? And why did you put this in here if you're not going to ask me a question about it? The reason why I put it in there is, you can probably guess what I'm going to say. The more that you understand how something works, the easier it becomes to memorize, why it does what it, or, the easier it becomes to memorize the reaction. Right? If you understand that you form the mercurinium ion that doesn't undergo a rearrangement, and you understand that the nucleophile is going to attack at the carbon that would produce the more stable carbocation, you're going to understand why you get Markovnikov addition with no carbocation rearrangement. And that's it, my friend. That's all you really need to know about oxymercuration, demercuration. Later on in organic chemistry 2, we learned something called, and you don't need to know this now, we learned something called alkoxymercuration, demercuration. So you can imagine that this reaction is a very important reaction. It comes up again kind of in organic chemistry 2. And yeah, so there we go. With all that in mind, question 8.12, it's not meant to be a trick question. It's not meant to be a confusing question. It's not meant to be a question that ruins your life. It's just testing you. It says, predict the product for this reaction, predict the products if an acid catalyzed hydration had been performed, rather than an oxymercuration, demercuration. Look, again, when we use oxymercuration, demercuration conditions, we're doing Markovnikov addition. However, we avoid any kind of rearrangement. So if we look at our alkene, we have the carbon in blue, we have the carbon in red. Can anybody tell me which one of these carbons would be the one that's going to take the hydrogen? Would it be the one in blue or the one in red? It is not a trick. Which one do you think it would be? The one in blue? Or absolutely, Bruna. 100%. Yes, yes, absolutely. All my students are 100% correct. The answer is it's the one that was in blue. So let's just write out the product. We don't have to take a lot of time to do it. We have our tert-butyl group over here, and we have our hydroxyl there. Done. Markovnikov addition, nothing to it. Now it says, write down what would happen if you had done an acid catalyzed hydration. Look, I think it might be handy for us to write out a mechanism. Okay, I'm not going to draw the mechanism for the first step because I don't want anybody to get confused with this. But in the first step, we get the Markovnikov addition of the hydrogen as going to the carbon that possesses the most hydrogens. And so we end up with this carbocation, which can undergo a rearrangement, right? This can undergo a methyl shift to give us this carbocation. So we have our methyl group here, and we have our positive charge here like this. So now we have a secondary carbocation and we have a tertiary carbocation. Well, technically, both of those could undergo the reaction to form the alcohol. Right? So if it was the one that's the secondary carbocation after the nucleophilic attack and proton transfer, so nucleophilic attack and proton transfer, you would end up with this alcohol, which is it's the same as this, but you would also end up with what? You'd also end up with this guy, okay, which is the product of Markovnikov rearrangement, or sorry, Markovnikov addition followed by the carbocation rearrangement. All right, so nucleophilic attack and a proton transfer there too. Give me a thumbs up if you follow me on that, because if you do, that means that you understand the whole idea of oxymercuration, demercuration very well. Great, great, wonderful. So look, memorize these conditions. Step 1, HgOAC2, H2O. Second step, NaBH4, sodium borohydride. Remember the AC, so OAC means this, oxygen, and then a carbonyl with a methyl group. So if you've ever studied acetyl coenzyme A, right, this is an acetyl group right here, okay? All right. except in acetyl coenzyme A, it's a thioester. So you have coenzyme A, and you have a sulfur, and then the carbonyl, and then the methyl group, like that. Anyhow, that's biochemistry. So let's not worry about that today. It's a different class, so I'll just erase that. All righty. Well, that covers all of section 8.6, and I want to move into the new reaction that we're going to use a heck of a lot in Organic Chemistry 1. We're going to use it a heck of a lot in Organic Chemistry 2, and it involves AntiMarkovnikov addition of water. Right? Remember when we wanted to do AntiMarkovnikov addition of HBr? Remember how we did that? We used HBr and an organic peroxide. Okay, that was for AntiMarkovnikov addition of HBr. But if we want to do an AntiMarkovnikov addition of water, okay, so if we want to add water in an AntiMarkovnikov fashion, we do something called Hydroboration Oxidation. Okay, so here's our alkene. This is the richer carbon. So instead of taking the hydrogen, that's the one that's going to take the hydroxyl. This carbon was poorer in hydrogen, so it's the one that's going to take the hydrogen. And the steps are BH3THF. So BH3 is borane. Okay, THF is tetrahydrofuran. Okay, which is this. Okay, it's just the cyclic ether, 5-membered ring with an oxygen in the ring. Then here we have hydrogen peroxide, and here we have sodium hydroxide in the second step. Okay, notice that this is a 2-reaction sequence, step 1 and step 2. So first step is borane and THF together, and the next step says hydrogen peroxide and sodium hydroxide. Now, if you're very astute and paying attention, you might have noticed something kind of weird here, that there's a dot kind of floating in the middle of the air, and you might have been like, what's up with that dot? Well, the reason for that dot is that it means that the borane and the THF, they actually react together to form what's called a complex. So you know that borane, BH3, you have boron with 3 hydrogens, right? It's sp2 hybridized, right? The boron has a steric number of 3, and so it has an empty p orbital, right? It's got an empty p orbital. I'm going to delete that. But then you have the furan, the tetrahydrofuran. It's got 2 lone pairs. So what happens is one of the lone pairs on the oxygen actually gets dumped into the boron like that, and you end up with this complex, which looks like this. You have the boron with the 3 hydrogens still bound to it. Then you have the oxygen in the ring here. So you have a positive charge here and a negative charge here. So we call that the borane THF complex. So we usually just call it borane THF is what we call it. So you borane THF followed by hydrogen peroxide and sodium hydroxide. This is another example of a reaction where the mechanism is covered in our textbook, and I do have it in here, and I'll talk about it in a little bit. So let me get onto it here. In terms of the stereoselectivity, we know the regioselectivity. It's AntiMarkovnikov, right? That's right back here. AntiMarkovnikov regioselectivity. But in terms of the stereoselectivity, the hydrogen and the hydroxyl are added in what's called a syn fashion. All syn means is that they're added to same side of ring, or the same face of molecule is what I should say. Same face of molecule. The reason I said ring is because I had ring on the brain here. I was looking at this. So again, you're doing the AntiMarkovnikov addition of water across this double bond, but the hydroxyl and the hydrogen are both going to be added to the same side of the molecule. Okay, so they're either both pointing up or they're both pointing down. You're never going to run into a situation where one is up and one is down, one is up, one is down. It never happens. Okay, so syn addition of the hydrogen and the hydroxyl means they're added to the same face of the molecule. I'm just looking at my notes here. I just noticed that I had some information about the borane. Okay, so borane again is BH3. So this again is called borane. Okay, right. If we look at the hybridization of the boron in borane. Well, boron is what? 1s2, 2s2, 2p1. So you have a 2s orbital with 2 paired electrons. Then you have a 2p orbital that has 1 unpaired electron. So you promote one of these over here, and then you end up with sp2 orbitals, 3 of them that are degenerate. You have unpaired electrons in each of these, and then you have a 2p orbital that's unhybridized, right? So that's what they're showing here. This is the 2p orbital, all right? And so that's why borane is a good Lewis acid. It can accept electrons from a lone pair on the oxygen in the THF molecule. So again, the boron atom doesn't have a full octet, so it can undergo what's called intermolecular resonance to help it fulfill all the octets. So it can form these what are called banana bonds. Banana bonds, they're 3 center 2 electron bonds. You know, I'm never going to ask you about a banana bond. The only reason I put this in here, okay, there's one reason. Okay, so pay close attention. It's this. It's that in our textbook, 100% of the time he writes borane THF like this, followed by hydrogen peroxide and sodium hydroxide. The thing is if you look at the ACS study guide or DAT materials or MCAT materials, etc., a lot of those study guides, they don't write borane THF. So if you try to do an AntiMarkovnikov edition of water and you don't use THF, the borane reacts with itself, and it's not shown here. It forms this, which is B2H6, which still works. So in the first step, a lot of times they just write B2H6, which means this is called diborane, okay? And then in the second step, they write H2O2 and sodium hydroxide. So again, if you have an ACS study guide, and I know some students have it, whenever you see B2H6, okay, so I'll just write it here in writing so that you have proof that BH3 THF is the same as B2H6. They both do the same thing, okay? They both just affect the first step in the transformation. So again, what happens is the B2H6, it can be stabilized by an ether solvent like THF. And so you form this active reagent here. And again, we just call it borane THF, okay, is what I call it. Borane THF. So borane tetrahydrofuran. Now the mechanism, okay, there's a disclaimer here. I know you're probably tired. It's a Monday morning. I've been lecturing for a long time. Just bear with me for a second, okay? The mechanism of hydroboration oxidation is covered in our textbook, okay? It's on the next slide. I would take a look at it. You don't need to memorize it because I'm not going to ask you to regurgitate the steps or anything like that. But what I would like you to do as a Chemistry 3101 student, as a 3000 level chemistry class, I think that every step in the mechanism should make some sense to you, right? The reason why we get AntiMarkovnikov Edition is this. What happens when you have an alkene and the borane, okay, what happens is that since the boron is electron deficient, right, the pair of electrons, oops, where's my red pen? And I know it's kind of written here, but the way I think about it is like this. The pair of electrons from the pi bond is going to want to dump electron density into that empty p orbital, right? But also, hydrogen is actually more electronegative. Hydrogen has an electronegativity of 2.1, and boron has an electronegativity of 2.0. I know it's not a big difference, but that means the hydrogen is going to be slightly, you know, wanting to take some of that electron density and dump it in here like that. So that's essentially what's drawn here. It's kind of like the same type of mechanism. But if you follow my 2 arrows, what would you end up with? Okay, my 2 arrows would take you right here, okay, where you have the boron attached to the least hindered carbon and you have the hydrogen on the more hindered carbon. So what happens is that happens over and over again until you replace each hydrogen on the boron with an R group like this, and then you treat it with hydrogen peroxide, sodium hydroxide, which again, you can take the time to look at. But anyhow, what happens is basically the boron is ending up on the less hindered carbon. I'm going to highlight that. The boron ends up on the less hindered carbon, and the boron is what gets converted into the oxygen of the hydroxyl. Okay, and so that's why we get anti-Markovnikov addition. Again, in terms of the stereospecificity, the hydrogen and the hydroxyl get added to the same face of the molecule. Okay, syn addition. Okay, but when you only form one chiral center, right, it wouldn't matter if the hydrogen added to which face of the molecule here, because it's not a chiral center. Well, in that case, you just end up with a racemic mixture, and that's it. All right, so let's take a look at an example here. Again, when you get two chirality centers, you would end up with a pair of enantiomers, right? And again, it's the result of syn addition. You see that you end up with a stereocenter here and here. Okay, so two stereocenters, but notice that the hydrogens and the hydroxyls that are added are both on the same face of the molecule. They're both either going back, like I have circled in blue, or they're both coming out towards you like I have circled in green. Okay, so that's in a case where you have two chiral centers. So with all that in mind, let's take a look at some examples here. We're taking borane THF followed by hydrogen peroxide and sodium hydroxide. So this is going to be an anti-Markovnikov addition of water. Okay, and we know that it's going to occur by syn addition. So both the hydrogen and the hydroxyl will be added to the same face of the molecule. Now, if we look at the molecule, the alkene, you see that you have a hydrogen here and no hydrogens here. Therefore, the hydroxyl is going to end up on the carbon that is richer in hydrogens. So if we write down the products, what are they going to look like? Let's draw the carbon skeleton, okay, like this. And we know that in one case, we're going to have the hydroxyl going back, and we're going to have a hydrogen going back like this, right? Syn addition. And then we're going to end up with another compound where the hydroxyl is coming out towards you, and this hydrogen is coming out towards you. Now, technically, there's nothing wrong with the way that I wrote them. There's nothing wrong. But the two carbons that I have highlighted in yellow, those are not chiral centers, are they? Right? Because they're on a cyclohexane ring. So we can delete both of those hydrogens. I'm going to do it just because I'm the instructor. If you left them in because it helps you understand it, no big deal. But what you essentially end up with is a pair of enantiomers. So enantiomers, like that. All right. Let's try it again. We look at the two carbons in our compound. This one has a hydrogen, so it's going to take the hydroxyl. We have a case where, let's draw the 5-membered ring like this. This chiral center is not going to be touched. We have a case where the hydroxyl is going to be coming out. We have and of course, that means the hydrogen is going to be pointing out, and that means that this methyl group would be pointing down like that. Now I can delete this hydrogen because this is a bond line structure, but I'm also going to have a case where, where I have my 5-membered ring. Again, this chiral center remains untouched. My hydroxyl is going down. My proton is going down. And my methyl group here is going to be pointing up. And so again, I can delete this hydrogen. And so what am I ending up with now? What would be the relationship between these two compounds? Could anybody answer that? What would be the relationship between these two compounds? Are these enantiomers? I don't think they are. They don't look like mirror images to me because this chiral center remained unchanged. What would the relationship be? Could anybody tell me? Yeah, absolutely. They're diastereomers. Diastereomers. Thanks, you guys. Great. Excellent. Excellent. You're both 100% correct. All right. So what have we covered since our last break? We covered Markovnikov addition that avoids carbocation rearrangement. So that was oxymercuration, demercuration. We looked at a practice problem that involved that. We saw that it's a two-step process. The first step is mercuric acetate and water, followed by sodium borohydride. Next, I'm going to skip ahead, and we talked about hydroboration oxidation. It's a two-step process. First step is borane THF, followed by hydrogen peroxide and sodium hydroxide. We saw that it affects a addition of water with anti-Markovnikov regioselectivity, and it occurs via syn addition. All right, there we go. So we talked about that in great detail. But with all that in mind, I want to move ahead and talk to you about one more reaction before we take another break, and that is catalytic hydrogenation. All right. So catalytic hydrogenation is the addition of H2 across a double bond, right? You know that H2, or if you just have hydrogen in the periodic table, right? This is hydrogen, okay? This is a hydrogen atom, but we know that hydrogen is a diatomic molecule, so we call H2 hydrogen as well. This is a hydrogen molecule, okay? If you have H+, we call that a hydrogen cation, but we usually call it a proton because that's all that's left. It's just the proton in the nucleus. And if you have a hydrogen with a negative charge, we call that a hydride. Okay, it's where the hydrogen has an extra electron. So what we're doing in hydrogenation, okay, is we're adding H2 across the double bond. So we're adding H2, which is this, across a double bond. All right. And in order to do this, it requires a metal catalyst. The metal catalyst can be palladium, it can be platinum, or it can be nickel. Not all three at once, not two at once, but it can be one of these at a time. So what happens is both of the carbons of the double bond, so the carbon in red and the carbon in blue, they both accept a proton, right? They both have a new proton attached to them. And so you go from an alkene to an alkene, right? We're starting it with an alkene, and we end up with an alkane. Okay, just like that. And you can see that this occurs with 100% yield. Very, very good reaction. So a very useful reaction. Now, what about the stereospecificity? There's no regioselectivity to take into account since we're adding the same atom to both carbons. But the stereospecificity is such that we have syn addition, just like we saw with hydroboration oxidation. So both hydrogens are added to the same face of the molecule. Here we have our H2 molecule. Either both hydrogens are going to be going down like this, or both hydrogens are going to be pointing up like that. Okay? Either way, both of the hydrogens are added to the same face of the molecule, and there's a very good reason for that. And I'll talk more about that later. Now, why do we need this catalyst, this palladium, platinum, or nickel? Because without it, hydrogenation is so slow because the activation energy is just too large. Remember from your general chemistry that when you add a catalyst, not only does it lower the activation energy, but it normally alters the pathway as well. Okay, so we get a different pathway, and it also lowers the activation energy. So we increase the reaction rate by quite a bit with the catalyst. Now, if you're wondering what the mechanism is such that the hydrogen gets absorbed on the surface of the catalyst. So you see all these black spheres down here? These are either the palladium, platinum, or nickel. So the hydrogen atoms actually get absorbed to the surface of the catalyst, and then the alkene comes down and it approaches the surface of the catalyst, right? And it's like this is a UFO landing down towards the surface of the Earth, and then it's abducting all the hydrogens that get attached. So all the hydrogens are getting attached to the same face of the spacecraft, right? They're all going on the same side, right? Why would some people enter through the bottom of the UFO and some people enter through the top? Makes no sense. People always get abducted through the bottom of the UFO, right? There's a little ladder that comes down, they climb up, right? Anyhow, you know, to show you using my hand waving method, okay? Where's my camera? Right, if you think about the surface of the catalyst as having all the hydrogen atoms on it, like imagine the palm of my hand. What happened there? Anyhow, if you think about the palm of my hand as being the surface, right? So the alkene, I don't have my model kit with me, but the alkene comes down and it lands on the surface of the catalyst. So the hydrogens are all added to the same face of the molecule. like that. So that's how the mechanism works. I know that might seem like a pretty silly way of explaining it, but that's the best I can do, okay? And in fact, that's a mechanism that I don't think was understood for a number of years. So, we have quite a bit of knowledge of it now, but that explains why the hydrogen atoms are added to the same face of the molecule, or they undergo syn addition, same face of the molecule. Well, if you start out with a symmetrical alkene like this one, you see that there's a plane of symmetry here. There's an axis of rotation. If both of the hydrogens are added to the same face of the molecule, look what happens then. You end up with a meso compound, right? So this is meso, and that goes all the way back to chapter 5. You always got to be on the lookout for that kind of compound. And so we end up with only one product in this case. The whole section about homogeneous catalysts, you don't have to worry about that at all. We don't cover that section one bit, so you can just skip anything about that. So if you have 0 chiral centers, syn requirement for the addition is irrelevant. You're only going to get one product. If you only have 1 chiral center, you get a mixture of enantiomers. And if you have 2 chiral centers, you get a pair of enantiomers. Well, with all that in mind, let's take a look at question 8.18. Comes straight out of your textbook. It's an excellent practice problem. It says predict the products for each of the following reactions. So we're taking this alkene and we're adding 2 hydrogens in a syn addition fashion. So let's draw what that would look like. I'm going to have my carbon skeleton like this. I'm going to draw both of the hydrogens going up. So I've got one going up here, and that means that this methyl group is going to be going down like that. Plus, I'm also going to have this situation where I have the methyl group coming up, and I have a hydrogen going down, and I have another hydrogen going down like this. Okay, there we go. Well, what do you notice about this? I notice that these 2 carbons that I'm highlighting in yellow are not stereocenters, are they? Those are not stereocenters. So I can delete both of those hydrogens, which I'm going to do just like that. And so what we end up with are a pair of enantiomers, right? So we end up with enantiomers. Could anybody tell me how many compounds I would get from this reaction, the second one? How many different compounds would I get from this reaction, from the syn addition? Yeah, thanks, Mackenzie. You're 100% correct. You only get one. Why? Could anybody answer why you only get one compound? I know you know the answer. Could anybody answer why we only get one compound? Syn addition, identical. There's a key word I'm looking for here. It starts with M and ends with ezo. That's right. You end up with a meso compound, right? So if I do a syn addition, okay, we'll write it out like this. If both of my hydrogens, let's say, are coming up like this, okay, that means that both of the methyl groups are going down, okay? And this is a meso compound. So if both of the hydrogens are pointing down, you still end up with the same molecule. Okay, so only one product in this case, and it's meso. All right. Here we go.